Hello, everyone, and welcome to today's session on model-based systems engineering, a critical enabler for digital transformation. This is part one of our three-part series. I would like to thank everyone for taking time and being here today. Thank you so much for being there. And just to let our audience know, we will be running a live Q&A session towards the end of the webinar. So you can ask your questions in the chat window. And if you miss anything, don't worry. We will be sending around the on-demand recording. This will be available directly in the email IDs for you. And I'm Sharath, working here at Trident Infosol. I will quickly walk you through the outline of the webinar today. There'll be a very short introduction about Trident Infosol, and then our speaker for today, Mr. Mudit, he will talk to you everything about the model-based systems engineering and the SysML. And towards the end, we also have some very interesting case studies that will be made available for you to download. So stay along with us and you will have some interesting case studies that you can actually download. Right, so just to start off with Trident Infosol, we started in 2000. We have offices across India, and we are known in the industry as a complete solutions provider. And these are some of the clients that we are working today. This is not the exhaustive list. These are some of the key clients that we've been working over the years, be it in defense or in the private organizations. And talking about the business verticals at Trident, we majorly have three verticals, starting with embedded COTS hardware, and there is embedded COTS software, and there is system solution. With all these three verticals, we are serving various industries starting from aerospace to medical domains. So moving along to the first group, here we work with a lot of single board computers. It could be the hardware available, the mezzanine cards, the daughter cards, and these are some of the companies that we work when it comes to the embedded COTS hardware. So you might recognize some of the names already. And the next one is, the next vertical is on the embedded soft, and predominantly the team that is responsible for today's webinar. Again, as what you see on the extreme left and extreme right are the partners that we work with. In the middle, you see the name of the products. At the center is obviously the entire engineering development cycle. So, we have solutions ranging from you defining your requirements to your system level specifications. We would be talking to some detail on that today. And yeah, when it goes to subsystem designs or the complete implementation, or be it in testing and complete hill validation. So we have solutions across all the verticals that you're working on. And these are some of the products that we are majorly working. And Deso being a premier partner, especially when it comes to the model-based MBSC framework. So Deso is a very important pioneer when it comes to MBSE. And the final division is where we have our in-house solutions. These are something that is custom built at Trident. We manufacture these, and this is also commercially available. And that's some of our facilities that we have at our office. Yes, I think we do a lot of webinars, and then it's regularly posted on YouTube. So I would suggest everybody to subscribe to our YouTube and LinkedIn. You will see a lot of webinars. Especially those part series of part one, what you're seeing today, you will also see the links for part two and part three as well. So you can subscribe to our YouTube and LinkedIn channels. And before I hand over my presentation to the speaker, I think I've spoken about these two companies, Deso Systems and Trident Infosol. Deso is a pioneer when it comes to MBSE. Another interesting one that you see is BlueKai. So BlueKai as a company, is into transforming businesses for technology adoption and integration. They mainly work in the area of digitalization, and so that's where their specialization comes in. And this is our speaker for today, Mr. Mudit Mittal. He's a technology director at BlueKai. Mudit is a technology director at BlueKai. He's got over 12 plus years of experience handling new product innovations. It could be the electronics, embedded software. He has led various designs, modeling, and I think he's known in the industry as an evangelist for MBSE, and that's the expertise Mudit brings on the table. He's also the technical officer at Incosi India chapter and also a co-founder at Incosi India in MBSE work group. So over to you, Mudit.
Thank you. Thank you very much. I'll just start sharing my screen now. Am I sharing my screen? Hello, can you see my screen? Can you please confirm?
Yeah, Mudit.
Okay.
Yeah, Mudit.
Okay, thank you. Yeah, so good afternoon, everyone, and welcome to the webinar. Thanks, Sharath, for a very good introduction of our company and myself. Before we move forward, we do have a couple of polls. We want to have them before we start the webinar, just to get a feel of who are the audience and what are their relationship with MBSC. So can I please request the polls to be out, please? Okay, that's pretty good. We have a very high number of people working, in engineering design centers. Okay, maybe next poll, please. Okay, and the next poll was your experience with MBSC, and we have a very good mix of people who are experienced and who want to get into MBSC. So that's a very good mix of audience we have today. Thank you. So I'll get started. That's me, and Sharath was kind enough to introduce me. I'll just quickly go over my experience. So yes, I am a technology director at Blue Key Solutions Private Limited with over 12 years of industry experience. And my focus has been on innovation projects, adoption of system engineering and capabilities in the enterprise. And by education, I have done my master's certificate in system design and management from MIT Cambridge. And I'm also a master's in embedded systems. You can find me on LinkedIn here. You can utilize the QR code below, and you can find me on LinkedIn. So before I get into the topic, I would like to briefly give you a background of Blue Sky Solutions. So our motto is transformation through systems engineering. And this is our mission. We empower decision makers in transforming business, in technology adoption and seamless integration of maybe your product lines or any other things through methodological and systematic approach. What we can do for you is we can manage the iron triangle of budget, time, and scope effectively. So if you have any issues in the process, if your time is exceeding or your cost is exceeding, we can have a look and we can give you suggestions for improvements. Provide actionable plan and support on pain areas in process and product development, and assist you in taking informed decisions. How do we do it? So we make use of the systems methods and process analysis. We provide digitalization support and system engineering competency development. And just a brief background of the team. So we are a team with collective 40+ years of industry experience. We are trained in systems engineering from MIT and Caltech and other prestigious institutes. We also have an outreach in international system engineering community like in COSE and other SE groups. So with that, I'll get into the topic for today. This is our agenda. So I'll be starting with the need for digital engineering. What is digital engineering and why do we need it? Then we'll be looking at what is MBSC. That is the core of the topic today. And then how that enables the adoption of digital engineering. Okay. So I'll be sharing a lot of anecdotes and images from different papers and online libraries. So this one is taken from NASSCOM. It's a very good article if you want to understand more digital engineering and opportunity and parallel. And this basically talking about that out of all the industries, the automotive industry is probably going to get the maximum adoption, the most highest propensity of digital engineering adoption, and at a very high scale as well. And probably because our focus on the electrification and automation or autonomy that is coming up in the next few years. And digital engineering, or what are the benefits? So the digital engineering has its own benefits, both on engineering side and business side, right? So through the adoption of digital engineering, there could be higher operational efficiency, better products, or you can reduce cost, ensure speed to market. But what it is really, really it is moving from traditional product development practices or engineering practices to digital engineering practices, like utilizing, moving from CAD/CAM or manual product design to actually simulation and AI-enabled generative designs. It could be moving from physical prototypes to 3D printing and computer integrated manufacturing. Moving from a manual documentation process to model-based process where everything's on cloud and everything is interconnected. So these are just some key technology enablers as you see below. But the idea is that digital engineering is coming and we all should be ready for it. So so this was all about the digital engineering, but I would like to bring our focus towards the systems engineering side of the overall digital engineering. And what you see here is most of you might already be familiar with. This is the traditional systems engineering view, where we start with needs for a product development and look end at a solution. And many times this is more sequential in nature than recursive and iterative. And it's actually celebrating its 30th year this year, this diagram of traditional system engineering view. But as we go into model-based era, what we need is a virtual twin of it. So yeah, so there's a digital twin that exists for whatever we do. There exists a virtual world, and just to give you an analogy, there's a symmetry between the bottom and top, in the left and the right. So for example, you would see that if you just look at the left side, if for your needs there exist system models, or even for your the planning there exists production models. Similarly, on the right side, let's say you have started doing physical integration. What you would do is you would first do virtual assembly and integration. You will try out things first in the virtual world, so that you can fail often, fail fast, but you built it only once or twice. Actually built it only once. So that's the idea. And so as I mentioned, yes, there's a symmetry both from left to right and top to bottom. And the idea is that it is completely iterative and recursive in nature. So if we take an example of manufacturing a car today, you could actually start with the customer needs, start looking at the various design, manage the variants and solutions and the various services that you want to give out, both in the virtual world, which will be a digital twin, and in the physical world. And that basically, the things that ties together is your digital thread. So together, this is sort of the new symbol or new framework that is going from traditional system engineering V to the document era or the digital thread, from the document era to the digital thread, called as the MBE Diamond. And this was introduced very latest in IW 2020 by Boeing. Okay, so with that, what I would like to talk about is why, or what are the various reasons, or what are the various complexities that exist in the product development. So this is taken from a paper where they gathered the data about a German automotive OEMs, and they looked at, back in 2000, they took about 10 years to manage 300 different model series. Whereas now in 2015, or 5 years back, there was a 40% reduction in the time to market, and there was 35% increased model series. So there was more complexity that they had to deliver in reduced time to market. Same can be actually looked at if you look at the Indian scenario. If you look at the example of Tata Motors or any other car manufacturer, maybe in the last 20 years, they have produced 2 or 3 different models. They might have different variants of that, but in the last 5 years, we have seen a tremendous increase in the number of models that have been coming to the market. Right, the Nexon came, and then the latest hatchback is coming. There are many cars that are coming. They have to manage these model variants every year. They might have to produce a new model every year. And if you look at it from a global perspective, companies like Hyundai, they still have to manage this at a very high level. They might be having same car but a different model name produced in US or being sold in Europe. So that's the level of complexity and the cutthroat competition that we're dealing in the today's world. This is another excerpt from Inkose System Engineering Handbook. It basically talks about for over the span of 140 years, where even though you were producing big systems like cars and different things, but their time to market wasn't that small. But now if you look at mobile phones, you'll see a variant coming every 6 months. So that's the level of complexity that we are dealing with. Okay, so we looked at two factors of complexity. One was the increasing number of technologies and the faster time to market. There's a third one, which is actually both a factor for complexity, but also an enabler. So it's the globalization. And with globalization, there comes diversity and geographical separations. So, we are able to divide work, get experiences of different people from different countries. But there are also challenges like, different spoken language and or IP issues or time zone differences. I personally, most of us have seen this issue or face a challenge when you're working one in India and the other person in the US. There's a huge time difference, and you're only able to have an overlap of a couple of hours maybe. So how do we all manage all this? So one thing that can resolve this issue or the challenge that diversity brings is the common language. So just as English has helped the whole, the world to be globalized or speak the same language, we need a common language for engineering, and that language then can become sort of a common standard or a common way to interpret designs and engineering language. The common language also captures great ideas and also captures experience, because people might come and go, but we need to capture their experience somewhere in a knowledge-based system. The second thing that can enable or resolve this issue is the engineering tool. We all know we are using a lot of engineering tools. What we need is an integrated set of engineering tools that can enable collaboration, that can manage the intellectual property. So you should be able to share as needed stuff with people you want to share with, and it also enables exchange of work. So sort of collaborating environment where you can work together. Okay, so I already talked about the tool and the language. The third piece that comes together and forms MBSE is methods. So together, tools, language, and methods form the pillars of MBSE or model-based system engineering. And I'll just give you some examples of what I meant by common language. So SysML or system modeling language is one of the most common MBSE language. And then there are also other languages like UML, object process methodology. Actually, it's a combination of methods and language. There are some examples of tools. You might be using many other tools as well. I'm just talking about Magic Draw here. The OpCat is a very good tool for OPM. And then there are also methods. So there are MBSE methods like IBM Harmony, Magic Grid, USUM. Also, there are many more. Capella has one. So these are various methods that basically ties the language and the tool together and then forms a workflow for you to create your MBSE artifacts. Okay, so here's just an official definition from Inkose. It's a formalized application of modeling to support system requirements, design, analysis, verification, and validation. So basically, it is going to help you throughout the life cycle of your product development life cycle. So what I'll do now is I talked about MBSE at large. I want to talk about SysML, a little bit about SysML today, just to give you an overview of what is SysML. Basically, it's a general purpose architecture modeling language, and it does not define any method or how to do it. It is just out there, and it's an extension of UML. So it extends from UML existing. It's a profile built on top of it. It was first initiated in January 2001, and it is now a ISO standard. And almost after 19-20 years of existence, there is currently currently version 1.6, and the team is now working on SysML version 2, which is going to be drastically different from the existing one, because The existing one is extension of UML. Now they are building it from bottom to up. It is going to have improved integration and analysis. It's going to support variant modeling, geometric views. It's going to have trait studies within and property-based requirement. And I guess they're also going to have open APIs so that it supports interoperability right from the start. So watch out for that. And it's a really exciting time about SysML coming up. Okay. So what is not SysML? And SysML is not a methodology or a software tool. We need to understand sometimes what happens is people talk about SysML is a tool, or I'm going to model that in SysML. Modeling is done by the tool. SysML provides semantics. Okay, so it's a visual modeling language that provides semantics, which means it provides a meaning, how you're going to do it, and then the notation, what is the representation of meaning. And I'm going to talk about these things as I share an example next. And multiple vendor tools support the SysML language. So there are many tools out there that can support this language. Okay. So SysML on high level is structured. It has 4 pillars. It can support structure or the physical domain. It supports the behavior of a system. You can write requirements for your system engineering, and then you can also do parametric evaluation. So you can create parametric diagrams. And as you can see, there is a cross-cutting relationship between all these 4 pillars. So the behavior is allocated to a structure. Then the structure has a value binding, so you can evaluate the different performance parameters of structure. And then you can evaluate requirements or verify requirements. And these requirements are then tied to your structure, behavior, and parametric models. So that's the relationship that we have in the SysML. And as I mentioned earlier, SysML is an extension of UML, and you can see from this Venn diagram that it utilizes some core concepts, whereas many of the concepts are also built on top of it. So we won't get too much into the detail, but here's a good eye chart to look about how things are in SysML versus UML if you're interested. Okay. So what I'll do is I'll be going into a smartwatch example. We are all familiar with smartwatch. This over here is a block definition diagram that basically shows the physical decomposition. And you can actually do logical decomposition as well. And I talked about semantics and notation. So over here it shows a filled diamond arrow that is connecting smartwatch to a watch module, which means basically smartwatch is composed of watch module, strap, button, back casing, and a glass case. And similarly, then watch module is further decomposed. So wherever you see this kind of a symbol, irrespective of which model you're working in, it conveys the same definition. And that is the meaning of having a common language or common semantic. This another diagram over here that I show is called an internal block diagram. And the idea is that these things are all interconnected via a modeling tool. So over left, you see a watch module that is decomposed into the CPU, display, speaker, sensor, and a battery. And the same thing you see over here. You actually see sensors, multiple speakers. And so this star refers to multiplicity. And then you have a display and a battery. And then you can also see the types of interfaces. You can actually see that you're able to model what flows between these sensors. So you're trying to build the architecture or the physical architecture of your system. You can utilize these type of diagrams to really show when you're working for your own projects. You can utilize these diagrams to show a context, or you can show a physical decomposition of systems. You can break down to as many layers as you want. And the IBD is used for your interface management. I have shown a very simple diagram over here, but it's capable of handling very, very complex interface diagrams. You can even define the system architecture of the interfaces, like, for example, if you have to model a laptop, you can actually say what's USB port it's going to be and what's the decomposition of that USB port. You can even tie requirements of those USB port, etc. So all of that is possible in this diagram. The second one that I talk here is called a behavior diagram, and there are actually 4 different behavior diagrams. So you have the use cases, you have activity, you have a sequence diagram, and state machine diagram. I have shown just example of 2 diagrams over here, but think of it like all the behavioral things that you have to define in systems engineering, like concept of operation or use case, OpsCon. How does your system changes its states over time? Or how are you going to describe the different sequence of events? So for example, on the left that I have here are different use cases from a user's perspective, right? So you can have different use context for your smartwatch. One of the use context for your smartwatch is the user is going to use it for daily commute or for daily utilization. Special utilization could be in healthcare. Another one could be for sports. So all these use cases you can define, then how are they going to use it? I have detailed out one of them onto the right, which is the activity diagram that I show especially for entertainment. So the same use case is further elaborated using an activity diagram where how a user is going to use this. Now, these diagrams are very, very much useful both while you have started working on your project, where you are in the problem definition phase. So for example, marketing is collecting requirements for your new product, or a user experience guy is trying to understand how the user is going to use your system. These diagrams are very, very beneficial even in the starting stage, and they can actually help you deliver needs, understand system requirements and your stakeholder requirements very early on. You can also use actually sequence diagrams. They are very, very helpful in understanding the exchange of information or how a user or multiple users are going to interact with your system. So just coming back to my diagram onto the right side, it's called an activity diagram. It's derived from UML activity diagram, but it's a very lightweight. It does not go in too much detail as UML diagrams go. But whatever here is, there's a decision making, and if the user wants to play a video, he or she would select the video app. Otherwise, if they want to play the music, they would select a music app, and then the play selected video or play selected song, and it will end. So it's a very simple activity diagram that I have created. The third one here I'm talking is a Smartwatch example of requirements, and most of you might be familiar with this, as many of us, if not everybody creates a requirement, at least all of us have to read the requirements that somebody else created in the product development lifecycle. And what SysML allows you is it has a very basic structure of requirements. It has a block called requirement, wherein you can give a name, an ID, and some text. But SysML language on its own is very much extensible. You can add a lot of customization, and whatever your process is, whatever your characterization or your attributes that you do in your requirements management, you can actually add them in a SysML tool. And you can then create traceability. So for example, I have tied my requirements here to different stakeholders like the business and the user. So for example, the business might want the smartwatch should cost less than, let's say, 10,000 rupees, or the smartwatch battery should last for 6 days without charging. So these are all business requirements or high level requirements that I have got for the designer. Okay, these might be coming from marketing or elsewhere. The user might have different requirements that are coming out of the use cases that we studied earlier. So you saw the different use cases here. Maybe pairing with devices was one of the use case, and I want to write or elicit those requirements. So we can think about elicited requirements, and you can create those relationship like trace, derived, copy. So I have a derived requirement which tells me that if I'm going to have pairing with the other device, that means I need to think about requirements such as the smartwatch shall support Wi-Fi or shall support Bluetooth 5.2. So I need to think about those requirements as well. And the last diagram that I want to talk is the parametric diagram. And this is again a diagram that is not existing in UML but has been added in SysML that lets you do calculations. So over here you might see a very simple calculation of total cost. Basically, it just adds cost of all the subsystems, and then outputs to the cost of the smartwatch. So this block over here is the smartwatch, and its property is called cost. And then each of the subsystems has a property called cost. But what it can do is actually you can have very, very complex calculations going around here. So you can tie your constraint block to MATLAB or even other different tools that can run your parametric evaluation and feedback to your models. There are many, many good examples out there where you can see, for example, you want to do some high fidelity models, like how much time does it take for a car to brake, like braking calculation. Or if you're designing a heat exchanger, you want to do some thermal engineering calculation. All you have to do is you have to pass those high level parameters from your architecture, and those calculations can then be calculated outside, and you can actually have multiple calculations running. Another important thing about parametric diagrams in SysML is that they are actually bidirectional. They do not talk about, even though my calculation says total cost is cost 1 plus cost 2 plus cost 3 plus cost 4 plus cost 5, I could actually enter this, and this, and leave out cost 5, and it can calculate cost 5 for me. So that's very interesting, that the way it is set up in SysML. But of course, it is enabled by the software or the tool that is doing the calculation for you. So yeah, and then the last thing that I want to show on the SysML diagram is bringing it together. As I told you, there exists a traceability, and none of these are done in silos. These all things need to tie it together and to make sense. So this was a smartwatch block that I showed you early, the block definition diagram. So the smartwatch has a cost constraint. There are calculations going on. It had different parts. It has a property of cost. And basically this cost is satisfying my requirement of shell cost less than 10,000 rupees, and which was coming from the business. So you can see that there is a traceability as we build across the life cycle. And the cost constraint is then on top of this cost value, which was calculated out in the previous diagram. So before I jump into summarization, there's time for another poll, and I would like to understand one more thing. So may I request for the next poll, please? Okay, thank you very much. So again, we have a mix of answers. We asked, how do you use MBSC, and then enable lifecycle modeling, or enable better engineering decisions, or high degree of reuse and communication. So yeah, actually all of them are the advantages, and there's a mixed response here. So thank you for your answers. What I would like to share is sort of to summarize what I shared so far. So we looked at the structure, we looked at the behavior. So we looked at how a smartwatch can be designed, it can be decomposed, how can we manage the interfaces. Then we looked at some of the behavior diagrams of how we can manage the use cases, operational concepts, and even internal behaviors of the system. We looked at how we capture the different requirements and the parametrics for the evaluation, and how all of these things tie together. So this basically is just talking about the same pillars of SysML coming together. Okay. So I think I quickly went through all the slides. Some of the advantages of doing MBSE. So you all have actually shared your experience on the vote. But just to summarize, I really like this principle of concordance. Basically, what it talks about is the model exists when you're doing modeling MBSE. The model exists in the tool, but what you see is just a visualization or a view. It's a diagram, so it's an abstraction. So think of it like a cube, and you can slice and dice it any way you want to create what you want to see. And that's what is called the principle of concordance. So you can have different levels of abstraction, you can create different views, different diagrams, for different stakeholders when you are working through MBSE, and that is very, very powerful thing. It actually enables reuse and reduces a lot of errors. So just when I was doing this slide, it might have happened that I would have written a word differently when I was in my slide 2, whereas write it differently in slide 28. But using MBSE, you can be consistent throughout because you are reusing your artifacts. It basically enables communication. So it communicates a system design effectively to an incompletely bounded audience, which means no matter if you are the system designer or you are a consumer of those models. So for example, it could be a program manager, it could be a third-party vendor that you want to share information with. All of them can be communicated effectively without having a doubt if they all speak the same language, and that's what MBSE enables. It enables modeling the life cycle, and that is again very important. You don't have to pick multiple documents for different phases of the life cycle. You can model everything together, and then you can generate those documents as you want to go ahead. It also allows automated reasoning. So that's another very, very important things that MBSE enables, is since you have the same language, which is actually computer readable, you can do reasoning on top of those tools. So you can do validation in modeling domain. So just like you can reason softwares, you can reason MATLAB codes, you can run many algorithms on top of your architectures that you have developed. Okay, so all these 3 domains, basically how you have modeled, what are the engineering things, parameters, like what are the performance values, MOEs, MOPs, you can calculate all of that. And you can also look at programmatic domain, like what's going to be the cost and schedule. Now, of course, you have to model project management pieces into SysML or MBSE tools for that. And it basically narrows down the risky and expensive gap between describing a design and analyzing it, because you are now able to do almost everything together in a single go. Then it enables decision making. So most often what happens is when we do concept generation, many of the concepts are in our head and we might note them out somewhere. They're lost in documents, or we are not very systematic about generating those concepts. You can actually do all of that in MBSE tools and then take informed decisions out of it, maybe through simulations or some other trade-based studies. Then, of course, I talked about complexity. So basically, it allows managing complex architectures by taking out the complicatedness. The complicatedness is managed by the tool. All you have to do is design the complex system. Okay. I would like to talk about some of the best practices from my experience. And this is a very important one. Start small. So most often what I have seen is people tend to convert their 3D drawings into SysML drawings, and which is a very, very risky affair. You end up having diagrams that have more than thousands of elements on the same sheet, or maybe thousands of different interfaces on the same sheet. So start small and keep it simple. Ask the right questions. That is very important. Why are you doing it? What is the purpose of system I'm modeling? You know, sometimes people model because they like to model, but that is not the purpose of modeling. The purpose of modeling is to maybe provide some answers, looking for interfaces, looking for complexities, resolving complexity. What is the purpose that you're having? And accordingly, you should model. Okay. What am I going to use it for? Who are the stakeholders and consumers of your model? Many times it happens that we have to put modeling artifacts because I was asked about it, or it also ties back to your purpose. So if the business is looking from programmatic or program management aspects, you might have to include those aspects in your modeling. Or if there is a person who's going to look at the simulation piece of it, or validation piece of it, include the test cases in your model. So those are all, look at it from your stakeholders perspective. And as I said, keep it simple. And one thing that I have learned from my experience is that leadership alignment is a must for adoption. So I know this is not a modeling best practice that I'm sharing, but if you're looking for MBSE adoption in your company or your organization, a leadership alignment is must, because it takes time. You have to be very, very patient when you are doing MBSE, because sometimes it could take years to show fruition. That's why you need to start small and have leadership in your alignment. And do remember that MBSE is to SE what CAD was to 2D drawings. It took maybe 30 years for the whole industry to go from 2D drawings to CAD. The CAD is today, where now it is inevitable. Everybody is using CAD. Same as MBSE. MBSE is coming. It's coming big way, and we are moving from document-based systems engineering to model-based systems engineering. So we need to be patient, and we need to be consistent and thorough when we are doing this. Now coming to the last slide, basically how MBSE is a critical enabler, tying all the things together. MBSE enables system engineers to be consistent, and that's the very, very, very important thing here. You also saw that digital engineering has a lot of many different moving pieces. The digital twin ties together across the life cycle. So you could be using various tools like a requirements management tool or an MBSE tool, or you could be using a PLM tool, and then some guys might be using validation verification tool, product planning or service cloud, those kind of tools. Unless and until you are consistent, there are going to be issues in tying all of these things together. And MBSE actually serves as a centerpiece, because you can actually model almost all the pieces of the life cycle within MBSE. And through interoperability, then it can become the center of information exchange through these multiple MBE tools, as I just mentioned. And I think the next phase in the information exchange is the OSLC. And also SysML v2 is going to enable a lot of open APIs that is going to enable interoperability. And finally, it brings rigor through methodology and concordance between various stakeholders of the program. So there is a view for everyone. No matter who's your stakeholder, you should be able to generate, or being able to generate, some automatic reports and automatic views out of your existing model. So I think I went really fairly quick, but we have about 10 minutes left. So with that, we can open up for questions. And yeah.
We will now go ahead and take some questions. We already have a few questions. This is an interesting one. If is system engineering as more related to the left side of the V cycle? How is MBSE methods useful to the right side, which means on the verification and the validation side? So in a nutshell, is MBSE useful in the right side of the V cycle? And if yes, how can it be useful?
Yeah, so yeah, as I mentioned, it's a very good question. It's, as I mentioned, MBSE actually enables a whole life cycle. You can actually, when you start on the left side, when you are writing your needs, when you are doing your high-level conceptual design, you're already thinking about how you're going to verify and validate it. So when I say you're already thinking about how you're going to verify and validate it, you are going to think about the various test cases that you're going to do. You're going to think about the various validation techniques that you're going to apply, right? Various scenarios in which you're going to validate your system. All of that can be captured within an MBSE model. You can actually model your test cases as use case scenarios. So when I showed you earlier, the use case could be as a for service center, or I talked about use context could be about for a smartwatch could be playing sports. Those are all that is when I'm thinking about the right side of the V, and I'm thinking how a user is going to experience it, and I can actually model those thoughts and actually test out those test cases within MBSE. I hope that answers.
Thank you. So there's another one. So is MBSE usually done by the automotive OEM, or even the suppliers can do it with the support from OEM? So who in the chain actually uses MBSE? So that's the question.
Yeah. Actually, again, actually anyone can use this. And I talked about the principle of concordance, and that comes very important here. So, for example, you are an automotive OEM, and you are thinking about, let's say, layer one, which is your car, and that you want to produce. You break down your car into different subsystems. Let's say your engine, chassis, and you're thinking about a specific engine that you want to procure from your vendor, right? So let's say then what you would do is you would design your engine as a black box, and you would write your interface requirements and your functional behavior of what the engine should perform. You're not designing your engine, but what your engine should do. And what you can do is then you can give, or you can share a sliced version of your model to your suppliers. You don't have to share your SRDs or PRDs, but you can actually share the whole model with them, or your what you call as a gray box. So there are three boxes: black box, white box, and a gray box. You can define how much you want to share, and that file then can be shared maybe through servers or offline, however you want to make sure that your IP is safeguarded. And then your vendors can always have the latest system architecture design that you have, and then they can carry on their work from there off. So basically what we are calling over here is you're handing off your system information across layers. So actually anybody can use it, and it becomes very, very helpful to check if there's a change that happens. So if everyone is connected, even your vendors are connected over a cloud, if a change happens, let's say 5 months down the lane, the vendor changes something or you change something, you are able to see what all things are impacted. So yeah, anybody can use it. Next question, please.
Yes, since you spoke about concordance, there's another question on that. Is it possible to explain concordance with an example? I mean, if the time is short, we could take this offline, but if you can take it now, Mudit, any example for concordance?
Absolutely. So basically what it is talking about is, I can quickly go back to my, oh, sorry. So I talked about this example that I'm sharing, the parametric diagram or any other diagram over this diagram. So you see a single view over here, which says smartwatch is composed of different subsystems. And then it shows that watch module is decomposed of various subsystems. If I was to share this model with my vendor who's going to produce, let's say, just the watch module, I wouldn't be giving all the complete detail of how the smartwatch is composed of different things, but I would just hand out this small portion. So what I would do is I'll create a new diagram that consists of only these views. That's the principle of concordance. For different views, for different stakeholders, I'm able to create different views. Similarly, I can just pick and select those specific use cases and behavioral diagrams that are important for me to share for that user. If I'm talking about a program manager who's interested in understanding how the project is progressing, I can just create a very high-level dashboard of, let's say, requirements and how are they being met with different validation and verification techniques. He or she might not be interested in understanding what are the interface, what's happening at the interface level, right? So that's how you can imagine your whole system engineering artifact as a cube, and then you can slice and dice it to create different views out of it. Yeah, that's in a nutshell concordance. Any more questions?
Thank you, Mudit. I think shortage of time, maybe we'll take two more questions. There is one question from Mr. Chandan. Will there be risk analysis tool in new SysML? Or the other question is
not fully aware.
Risk analysis semantics, correct? Yeah, so risk analysis semantics.
Yeah, unfortunately, I'm not fully aware of that, but I think we have that. Yeah, I'm not fully aware of it. We can get back on, get back to you on that. Sure.
Right. So there is another question. How is the time to market figure reduced using MBSC technique?
Okay. Yeah, that's very good. I will actually utilize this symbol. I'll come back to this symbol as this one very important thing in this diamond that is not shown, and that is that the lower V is the physical development, but the top V is actually the virtual development. And both of these have different timelines or different clock speed, if you will. So the idea is that you fail fast and fail often in the top half, but you do it only once physically. So you are able to generate, simulate, validate, integrate all of that in the virtual environment over hundreds and hundreds of times, much faster in the early on in the life cycle of the production. Because if you try to do a change after, let's say, your low production build of, let's say, you produce a small 100 number of cars, and then you figure out a problem, or your car is already out in the market, and then there comes a problem, there's a huge cost and time issue in your process, right? But if you're able to find those issues, you are able to avoid those risks by understanding everything early on in the virtual environment. That's how you can reduce the time to market and reduce the cost.
So Mudit, the next one is not a question, but it's more of someone wanting to know your experience on how, if you could give any examples from your experience on any crucial business or technical decisions taken through help of MBSE.
Sure, sure. So in my experience, I have mentored a lot of people on innovation projects utilizing MBSE. And unfortunately, I won't be able to give out the exact details, but it was in an off-road sector, in the agriculture sector. We were trying to improve the performance of a planting solution, and we went over multiple iterations. But the biggest thing in doing MBSE that helped us was the initial piece of understanding the context, understanding the concept of operation, tying all of those things with the needs, the actual needs of the system. So usually what happens is people come up with the solution first, but we took them back by understanding all these behavioral aspects using model-based systems and engineering diagrams and models. And they were a very, very important piece even for our communication with our stakeholders. So we were a team based out of Pune, and the other team, the stakeholders, were based out of US. And that model actually helped us communicate very effectively. Second thing that model helped was in the concept generation and evaluation. So we were able to model different alternate architectures for that innovation project, and then evaluate them. Some of them were evaluated within the tool, some of them were evaluated outside of the tool. And then later on, the third piece, the actual validation, we had a lot of number of design for experiment carried out, which were then tied back to our MBSE project. So that's one example that I can give from my experience. And I'll be happy to talk more about it if you want to connect with me later on.
Thank you, Mudit. That was very interesting. Mudit, I think I wanted to close on the question, but I think we've been talking a lot on automotive. So we have a question from aerospace industry. Is there any small example that you could on how MBSE would help in the aerospace industry?
Well, interestingly, system engineering originated from aerospace, and even this diamond that I show is from Boeing. So MBSC is a very, very important piece in the aerospace industry, and with the level of complexity that you have to deal in aerospace, the critical systems that you have, I think it is very, very important that you model everything. You don't want to leave any stone unturned in those critical situations. So for example, you want to start with all your features and your functions that you want to deliver. And then for the electronics part, especially, you have those very stringent requirements, right? 26262 standard that you want to verify and validate all your safety critical systems. If you model all of these, you'll be able to make sure that you are consistent and you are sort of testing and verifying everything. So I think, yeah. So it's very, very useful in actually any industry, I would say.
All right, I think it looks like we have covered all our questions. Mr. Mudit, is there anything else you want to cover up before we wrap up?
No, I think I'm good from my side.
Great. Thank you, everyone. Just a small note, on the right side of your window, you would see a section called handouts. So that is where you will be able to access one of the case studies. It's an aerospace case study that is shared. You could get an insight as to how MBSE has helped here. And our team will reach out to you for sending you the webinar links for the next series, this was part 1. So stay tuned with us for part 2 and part 3. So our team will reach out to you very shortly.
Yeah, and here's my email ID on the screen. If anybody wants to get connected, I'll be happy to chat. Or you can also find me on LinkedIn and we can connect over there.
Sure. And any questions unanswered, we will take it offline. So we will come back to you with the answers as well. All right. Thank you, everyone. We appreciate you being here. So have a good day.
Yep.
Bye.
Thank you.